So we now have Georgios Batzolis from the University of Cambridge, who will be talking about Variational Diffusion Auto-encoder, latent space extraction from pre-trained diffusion models. Thank you.
Hello, everyone. I'm happy to present this recent work of ours, which is essentially about combining variational autoencoders with diffusion models, with essentially the aim of making the variational autoencoders more expressive. That was like the original motivation. This is a recent work with Jan Stachuk, joint work, under the supervision of our supervisor, Karola Shunlib. So let's just discuss the basics for shortly. Here we see the design of a classical variational autoencoder, where you have the typical encoder and the decoder. And here we also see like the classical image about diffusion models from Tong, where you have the forward SD and the reverse SD, and like the whole point is that you need to approximate the score function so that you can construct the reverse SD and be able to generate samples. The idea that we had back then was that can we somehow combine them so that we can improve the flexibility of variational autoencoders? Because like we have some classic problems that we have to face in variational autoencoders that I will describe now. So the variational autoencoder models the encoding distribution Q phi of Z given X and the decoding distribution P theta of X given Z. And how it does that is that it is usually trained using the variational lower bound, like the elbow. And the elbow contains two parts, the likelihood term, which is the expected log likelihood of the decoding distribution of X given Z under the expectation of the encoding distribution of Z given X. And you also have another term, which is the one shown here, the KL penalty term. And essentially this regularizes the latent distribution. It basically pushes the encoding distribution to be closer to some prior distribution that we choose. And the usual choice that people make for that is the Gaussian distribution, but this is not restrictive. You can choose other distribution as long as you can evaluate the KL between the encoding distribution and the prior that you choose. And they typically weight this by a regularization term beta. And the way they do that, the reason they do that is that if you like the theoretical choice should be beta equals 1. But when you choose beta equals 1, then when you look at it, like when you encode the image, you get the latent encoding, and then you reconstruct using the decoder, you're going to have like a very bad performance because the regularization ends up being quite strong. So they just choose smaller values of beta so that they can still regularize the latent distribution a bit. The standard assumptions that people make about the decoding distribution is that it is a Gaussian distribution whose mean and covariance are outputs of a neural network, which is essentially the outputs of the decoding network. And another assumption that is typically made is that the covariance matrix of the decoding distribution is just isotropic. It's just sigma squared times I. And usually sigma is also chosen to be 1. These are standard choices made in sort of like the vanilla VAE case. And the encoding distribution is also Gaussian, and the mean and the covariance matrix are essentially determined by the observation X. And they're essentially the outputs of the encoder that you have. Under those assumptions, it is easy to see that the elbow simplifies to the addition to these two terms. The first term is essentially the log likelihood term, but it simplifies essentially to an L2 term because we make the Gaussianity assumption about the decoding distribution. And then the second term is just the KL penalty term just expanded out. The standard problem that we see in vanilla V is the following. You see the original image, and these are examples from CIFAR 10, and these are examples from CELEB. we see that you have the original image, and then on the right you see the reconstruction, where you just have the image, you encode it in the latent space, and then you decode it, and this is what you see as a reconstruction. And the standard problem is that these images are usually over smoothed and blurry, and they are not representative of the original sample that you got. And this is for like beta equals 0.01, like for higher values of beta, it will be even worse. And the smoothing or like blurriness effect that typically is shown in a vanilla VAEs arises, I think, due to the decoding distribution assumption. We make the assumption, as I said before, that this distribution is Gaussian, right? And not only Gaussian, usually they also make the assumption that it is isotropic Gaussian as well. But even if you choose anisotropic Gaussian, you would still see problems, I think. And the thing is that this simplifies the likelihood term to the null2 reconstruction term. And this leads to oversmoothness because this is not a very realistic assumption of the decoding distribution. And people, what they do end up doing at the end is that they don't even sample from the distribution. They just output the mean. Because if you don't output the mean and actually try to sample from that distribution, you will see just the mean, which is the blurry thing, but then just noise. So it will be pretty bad. So people just output the mean and then they're happy with this. But I think we can do better here, especially with the use of diffusion models. So the idea we had back then was that we can essentially model the decoding distribution p theta of x given z using a conditional diffusion model. But then we were a bit sad because we realized that people had done this before us. In this paper here by Prince-Akul, they essentially proposed that. They proposed that the decoding distribution can be modeled by a conditional diffusion model S theta, which takes as input the perturbed observation xt, the latent encoding z, and the diffusion time. And this will be trained to approximate the gradient of the log density of xt given z, the perturbed observation given the latent encoding. So if we consider the standard forward process that we have in diffusion models that maps the observation distribution P0 to very close to some distribution PT, which is going to be very close to the prior distribution, the stationary measure, then it can be proven that the log likelihood of the observation x0, now I just I changed x for x0 just to move to the diffusion model setting. So x and x0 are the same thing. So the log likelihood of the observation x0 given z under the decoding model parameters, which are the parameters of the diffusion model, this is essentially equal to a constant c, which is this long constant here that doesn't depend on the parameters of the model, minus 1/2 times the weighted denoising score matching loss. And this is a typical weighted score matching loss. And the only difference from the unconditional case is that the conditional diffusion model will also take as an input the latent z. In this parameterization, I consider S theta to be the score model, not like noise predictor or the other parameterization. This is the score. This is trying to approximate the score function. So that is the log density of the observation given z, given the latent encoding, under the diffusion model parameterization of the decoding distribution. So the idea is that we just plug the diffusion-based parameterization of the log density into the elbow. So if we remind ourselves, this is the elbow, this is the likelihood term, and this is the KL penalty term, and we have an expression for the log likelihood of x0 given z, so we can just plug it in here and use the elbow to train the encoder and the decoder. In this case, we still use the standard Gaussian encoder, Q phi that we had before, and the decoder is the conditional diffusion model. So this part goes in here and we get samples from the encoder. And we can train both the encoder and the decoder jointly using essentially the elbow. And our colleagues essentially trained the encoder and the decoder in that way, but they didn't use KL penalty. They set beta to 0. And at some point, I just started running the experiments to see what happens if you increase beta. And I realized that this model, as it is formulated right now, it doesn't seem to converge for beta greater than 0. And I'm working on understanding why it doesn't, but it doesn't. And I can show you some samples now. So this is the original image you have. This is the reconstruction for beta greater than 0. This for reconstruction for beta equals 0, and that is the vanilla, and then the other one is the vanilla V reconstruction. And you will see that actually when you use the diffusion decoder with beta equals 0, performs much better than the vanilla VAE, because it does produce sharp reconstructions now. But there is the problem of no convergence for beta greater than 0. We also have examples for CLB, where you see that the reconstruction is actually, I think, much better than what you see in a vanilla VAEs. But we still have the problem of no convergence here for beta greater than 0. So to summarize, the diffusion decoders, I think, is a very interesting idea because it allows you to overcome the problem of oversmoothing. And essentially, another important note here is that the dimensionality of the latent encoding is of the same dimension, is pretty small. Because like you can have like VQVAEs, for example, which have like a much bigger latent encoding. So that it kind of makes sense that if you have like a much bigger space to compress, then you might be able to actually construct better. But in this case, we should also make it clear that we have the same latent dimension as we had in vanilla VAEs. So the increase in performance doesn't come from increasing the latent space, it comes only from increasing the flexibility of the decoding distribution. So the diffusion decoders overcome oversmoothing, and they don't converge for beta greater than 0, and we don't know why. But they also have another weakness, which is that computational efficiency. Essentially, because the decoder is a conditional diffusion model, you need to train a conditional diffusion model from scratch, so it is more expensive than training a vanilla VAE. And there is also not clear way to leverage pre-trained diffusion models on the observation distribution. So we started from basically improving upon this work. And the first straightforward improvement is that we can leverage pre-trained diffusion models. And this is pretty straightforward, actually. As I said before, the diffusion decoder, which is this score model, approximates the gradient of the log density of xt given z. And essentially, you can write this down as like the sum of the unconditional score plus this correction score, which is the gradient of the log density of z given xt. That is just Bayes' rule. And the important observation is that this part doesn't depend on the latent encoding. So we can use a pre-trained diffusion model for that part, or we can train our own unconditional diffusion model for that part, because essentially we don't need to learn that. You can learn this a priori. And we parameterize the score model as a sum of the pre-trained score plus the correction score that we learned during training. So right now, we train this at the start, or we just use a pre-trained diffusion model that approximates the score function. And then this is frozen during training. So we only learn this part, the latent correction part. And this improves optimization, given the complexity of optimizing the diffusion decoder and the encoder jointly. Because right now it basically does the job of the decoder easier. Because it only leads to, because in the previous case, you had to learn that part and that part while the distribution of the encoder was changing. It's basically like learning the conditional diffusion parameterization while the encoding distribution is changing. So this is just simplifying things. And the second improvement we had was that we realized that you actually don't even need a a conditional diffusion model. At the end, we realized that you just need an encoder and a pre-trained diffusion model to train the variational autoencoder. So if we see the elbow again, we have the likelihood part and the K penalty part. And in the likelihood part, we plug in the diffusion-based parameterization of the log likelihood. And having that in mind, we can see that if we fix the parameters of the encoder phi, then the maximizer of the elbow will be written in that form shown in equation 3. It will be essentially the pre-trained score, like S theta star will be essentially the pre-trained score plus the correction score of z given xt, but the optimal correction score. And the optimal correction score is given by that expectation. Essentially, if we think about it, you have like x0, which is the observation, then you have the encoding z, and then you have xt, which is the perturbed x0. And essentially, they're both connected via x0. Both xt and z are connected via x0. So what happens is that the distribution of z given xt will essentially be the expectation of the density of z given x0 under the reverse perturbation kernel, just because they're essentially connected via x0. And that would be the optimal correction score for fixed encoder weighting. And as we can see, the encoder distribution is Gaussian, right? So that part is Gaussian by construction. And for small diffusion times, the optimal distribution, the optimal density here, will essentially be quite close to the encoder density of z given x0 hat, where x0 hat is essentially the mean of the reverse perturbation kernel, which is x0 given xt. So since that distribution will be Gaussian by construction, also for small t, the optimal correction distribution will also be Gaussian, or like very close to Gaussian. And for large t, for large diffusion times, the latent correction score is insignificant. Doesn't really play any role because the pre-trained score dominates. And based on these 3 points, we made the assumption that the correction distribution p theta star of z given xt is Gaussian. So essentially, making that assumption, we parameterized that distribution using a time-dependent encoder. The encoder will just output the mean and the covariance of that distribution of z given xt. It will take as input xt and time, and it will output mu theta and sigma theta. And under this assumption, then we can evaluate the correction score, which ends up being just this essentially the gradient of this quadratic term that comes from the Gaussian assumption, and we just evaluate this using autograd. And also, it is easy to see that for t equals 0, the optimal correction distribution will be equal to the encoding distribution. So we essentially only need one time-dependent encoder for modeling both the encoding and the decoding distribution. For time 0, the encoder will parameterize the encoding distribution of z given x0. And for time t greater than 0, the time-dependent encoder epsilon theta parameterizes the latent correction in the score function of the decoding stochastic differential equation. And so what happens at the end, to summarize, is that this time-dependent encoder is the only moving part in the training process, because it gives you both the encoder and it also gives you the decoder as well, because it gives you this latent correction part, which when you combine it with a pre-trained score, this gives you the decoder. So there's only one moving part now, the encoder. And that's how we train the variational autoencoder. And you can also essentially think about this as also like sort of like extracting a latent space from pre-trained diffusion models. And we call this method score VAE. And an interesting question would be that we make this variational assumption right here. We make the assumption that the correction distribution is Gaussian, right? And initially we want to find out how good that approximation is, because this is essentially the only approximation that we're making here. It certainly introduces a bias, and there is a way to actually quantify the bias. What happens is that we train the encoder, and after we train the encoder, we freeze both the pre-trained score and the score coming from the encoder, and then we model the conditional score function of the decoding distribution using the pre-trained score, the frozen score coming from the encoder, which is our approximated correction score. And then we also add an auxiliary score here as C, which is another diffusion model. So at the end, we just trained the correction model using weighted denoising score matching, because this should basically correct for the errors made by the encoder assumption, by the variational assumption. And then we train using that just to quantify the error. And this is on CIFAR 10. And what I plot here is that essentially the relative magnitude of each component of the score to the total score. So we have three components here: the prior score, the encoder score, and the correction score. And I just plot the magnitude of the pre-trained score, for example, to the magnitude of the entire score. And this is what we see here. With green, you see the prior score contribution. With red, you see the encoder score contribution. And with blue, you see the corrector score contribution. And you will see, and on the x-axis, you see the diffusion time. So like for most of the diffusion range, actually, the prior score dominates. It gives you most of the information that you have. And then as you go closer to the data manifold, essentially close to time zero, you will see that the encoder score is still much bigger than the corrector score. So the correction only accounts for like some small part of the diffusion range close to the manifold. And also like looking at basically the relative performance of the score VAE with like the correction, the performance is very, very close also visually. So it doesn't really seem that the correctors help that much. So we believe that because of that graph essentially, and also the relative performance between the two methods, which is like almost the same, we believe that the variational assumption is actually pretty good. And also for the theoretical reasons I explained before. Now I will present some examples that we have here. Here we have again the original images, and these are the outputs of our method, score VAE, and this is score VAE with correction. For this kind of resolutions, you wouldn't see any difference, I think. And these are the results of the diffusion decoder, where it doesn't converge for beta greater than 0, and it converges for beta equals 0. So basically, I think like these methods are essentially equivalent for like beta equals 0, and our methods work also for beta greater than 0. And these are results on CLB, where you see that score VAE gives sharp reconstructions and essentially on par performance with the diffusion decoder, but it also allows for like regularizing the latent space. These are just some quantitative results that we have on CIFAR 10 and CLB. We essentially measure the reconstruction. You see the L2 reconstruction, the LP-APS reconstruction. In terms of the LP-APS reconstruction, score VAE performs the best, and that score seems to correlate better with human evaluation of distance between images. And yeah, we only have the case where like the actual VAE, vanilla VAE, performs better in terms of L2 in CLB, but I think this is not the best metric that you can use for evaluating the image distances. These are results that we have. These are recent results on FHQ. On the left, you see the real images, and on the right, you see the reconstructions from the score VAE method. And I would say they're actually pretty good because what would you get with a normal VAE? There would be something much blurrier than that. Whereas, like, I think these images are actually very close to the original ones, and they're also very sharp, like they are actually on the manifold. To summarize, in this work, we essentially propose a new method for training a variational autoencoder using only an encoder and a pre-trained frozen, essentially, diffusion model. It solves the problem of oversmoothing of vanilla beta VAEs. It performs on par with the diffusion autoencoders, and it resolves the problem of non-convergence of diffusion decoders for beta greater than 0. So it allows for regularization of the latent distribution. And it can also leverage expressive pre-trained diffusion models. Because, for example, if you have, for example, a very complex distribution like ImageNet, you don't want to also learn the pre-trained score of ImageNet, right? But that's going to be expensive. And it will be computationally heavy, and you won't probably be able to approximate it as well as other people have done it in like big companies, for example, where they have like huge compute. So you can just use all of that compute done by others, and you can basically train your VAE using only the encoder and the pre-trained diffusion model that you get from like free with the internet. Yes, essentially, these are the contributions of this work. And this is also work in progress right now. Essentially, we have seen that the model works really well, especially like in reconstructing images. We now need to work more on sort of like the use of the latent space, like because you also have like you extract the latent space and you can use the latent space for different tasks. You can do manipulation, you can do editing, you can do all of these kind of tricks that we see, for example, in the GAN literature. And essentially you can do all of these tricks using the latent space that you extract from the diffusion model. And this is something that I need to work on now. And I don't have like too much time in my PhD, so I also don't have a lot of bandwidth because I am working on like other projects as well. So if anyone is interested in collaborating in that part of the project, I would be more than happy to discuss. And yeah, the end of my presentation, basically.
Are there any questions? Yes.
Yeah, so do I understand correctly that this is